Hello, welcome back. In this segment, I wanted to answer this question. Can we factor a given composite number using primality testing algorithms? In particular, using the Miller-Rabin algorithm that we have been playing with. It is natural to ask because primality testing algorithms are able to tell whether a given number is prime or composite. So if they are telling us a number is composite, that means they were able to find some properties, right? So I'm going to ask this question. From Miller-Rabin algorithm, can we factor a given composite number? Okay. Your gut feeling must be telling you the answer should be no, because otherwise RSA and many other cryptographic systems are broken. But let us try to reason about Miller-Rabin in particular. Okay, let's bring up the table that we have been playing with for a composite number 21. Okay, so let me show you the table for 21. Okay, here is the table for 21 that we have been analyzing. And let's quickly recall how we do primality testing in the context of Miller-Rabin. Okay, so what we do here is that we take the number n, which is in this case 21, right? We write, I'm going to use small n in this presentation. That doesn't matter. Both capital N and small n are interchangeable unless I tell you. Okay, so is equal to 2 times r into u. Okay, how do we write this? N is 21. 21 minus 1 is 20, which means we can write it as 2 power 2 times 5, right? So R is 2, U is 5. Okay, R is 2, U is 5. So we will look at the sequence. What sequence are we going to look at? We will look at the sequence A power U, okay, A power 2U, A power 2 square U, all the way until A power 2 power R minus 1 U, right? We don't need to go to A power 2 power R U, but let me just write it here for the sake of completeness. What is 2 power R times U? 2 power R times U is nothing but n minus 1. Okay, so anyway, what is the constraint in the context of Miller-Rabin? For a number A to be witness, this A power U, this particular thing, must be not equal to plus or minus 1. Okay, it should not be equal to plus or minus 1. This is something we have already proved. And the rest of the numbers here must be not equal to minus 1. All right. If we find such a, then we say A is a witness for n. N is a composite number. Okay. Now let's think about the scenario here. Let's say A is 8. Okay. So which element of this row we will be looking into? We will be starting here because this is the 5th element, right? We say U is 5, and remember A power U is the one that's starting. So we'll be looking at 5th element and then the 10th element. Okay, what is the 10th element? It's the 10th element, which is 1. This is 1. And we also look at the 20th element. Okay, the last element, this element. Okay. All right, so let's pay attention to the 8 and 1. Okay, from 8 we square, we get 1. 8 square is 64. 64 mod 21 is 1. So what did we find? We found out something interesting. We found that 8 is actually square root of 1 because 8 square is 1. Okay, 8 square is equal to 1 in mod 21. Okay, so I'm not writing mod 21 again and again. So what is this telling us? This is telling us that we can factor the number easily because 1 itself is a square number, right? 1 is nothing but 1 square. In the previous segment, I proved a theorem that if we are able to find two numbers x and y such that x square is equal to y square in mod n, we can factor n by just doing a GCD of x plus y with n. Okay, x is 8 here, y is 1 here. Just an example. So this means that there are cases where Miller-Rabin algorithm can factor our number n and give us the prime factors. Okay, but the probability of that happening is almost close to zero for large numbers. Okay, otherwise RSA is broken right away. So this particular property may not be happening for large numbers. Okay, or put it other words, if the number n is very, very large, it's difficult to find a witness such that the one element, like for example number 1 here, is a square of another element. Okay, in such a way that we can factor. Okay, that's not easy. So let me summarize what I have been talking about so far. I'm going to look at the sequence, right? A power u, a power 2u, a power 2 square u, and so on. And if I find two numbers, say for example, I put it here, a power 2 power iu, right? How did I get a power 2 power iu? By just squaring the previous term, which is a power 2 power I minus 1u. Let's assume a power 2 power I minus 1u is not equal to minus 1, but we square it, we get a 1. Okay, that means we have a scenario like this. We found two different numbers, okay, such that the squares are equal. Then we can factor. Okay, now let me show you some experimental results for different numbers. Okay, all right. So let's try. I have my number utils. I will import that. Let's generate some numbers and see whether we can factor. Okay. As a matter of fact, why don't we try 21? The number that we are going to try is 21. We say is prime Miller-Rabin, right? 21, and let's try 40 try. Well, let's try a small number of trials, 10 trials. Yeah, right away it found a witness. It found a witness and it found a factor. Factor is 7. Okay, remember, finding a witness is different from finding a factor, just to be clear. So we are able to find a factor in this case, which is true because 7 is a factor of 21. Let's try one more time. Okay, we get 1. We get 3 now. 3 is another factor. Okay, so there are cases where we find factor. Let's try something more complicated. Say, let's generate some numbers. For example, let's create a random prime. Okay, 5-bit random prime, just 5-bit. I'll show you what that is. Right, this is 5-bit, and let's generate another prime 5-bit. Okay, so I generated 2 primes p and q. And now let me multiply these two numbers to generate a composite number. Clearly, n is a composite number. Let's see whether Miller-Rabin can find these prime factors. Okay, first of all, it needs to tell that number n is not a prime number, meaning composite number. Let's try, since it's just such a small number, so let me only try 10 trials. Okay, it says the number n is clearly not a prime number. And let's keep trying. Let's increase the number of trials and see whether. No. Yeah, well, if I increase the number of atoms for such a small collection, it is able to find a factor. The factor it is saying is 31. Okay, 31 is a factor. Okay, let's do one more thing now. Let's create something much bigger. Rand prime. Let's create a 10-bit prime and another 10-bit prime, right? And multiply it. And it says false. Okay, false. So it clearly says it's not a prime number, but it was not able to tell us the prime factor. Why don't I write a little loop and see whether somewhere in the loop it is able to successfully find the factor. Let me run this 25 times. Okay. 30 denotes the number of trials. Okay, the T. If you have to watch the Miller-Rabin algorithms, I explained the idea. Okay, so in all the atoms, it's printing the number n is not a prime number, but it was never, as far as I can see, never printed the prime factors. Okay, so this is telling us that there may be cases where Miller-Rabin can print the prime factors, but that's very, very rare. Okay, that's the very first thing. And I only talked about comparing a sequence of numbers and checking whether we get a 1. Right, we can generalize it to any other square number. Okay, let me do that now. So let me print the residue table for 21. And let me show the complete table. Okay. If you look at the number 4, for example, okay. Remember, we need to take the 5th entry, 10th entry, and 20th entry. Let me circle those entries. 5th entry is 16. And the 10th entry is 4. In the previous segment, we talked about how to find the prime factors when x square equal to y square. Okay, let's see what that is. We take 16, 16 square. What is the value we get? We get 4. And 4 is nothing but 2 square. Okay, so here you go. Here is your x and here is your y. So all you have to do is just take GCD of x plus y. So GCD of 21 with 18 will give you one of the prime factors. GCD of 21 with 14 will give you another factor. Okay, you can do either of those. So remember the previous segment, we talked about that. So there may be cases you don't have to only focus on finding square root of 1. Okay, here is, for example, 8 is a square root of 1 and in mod 21, and 16 is a square root of 4 in mod 21 because 16 square is giving you 4. Okay, so if you are able to find pairs of squares, then you are able to break it, meaning find the prime factors. But as I shown in the previous demo, very briefly, it was difficult to find the prime factors through Miller-Rabin. There may be cases it does show us the prime factors, but it's very rare. Okay, so let's increase the bit size and try and convince ourselves that's the case. Okay, let's do that now. So let me generate 2 primes. Let's say I generate a random prime of 128-bit, which is quite big. I mean, compared to public key crypto system, it's very small, but for quick demo, that's perfectly fine. Let's try now p times q. Okay, we can now ask Miller-Rabin, is prime Miller-Rabin n, make 40 atoms. It's clearly saying it's not a prime number, but let's run it in a loop 100 times. Whether it can factor the number and tell us the prime factors. Clearly, it's not going to work, but I wanted to convince myself and you. You see here, it's false, false, false. In all the attempts, it was able to tell that the number n is a composite, right? Meaning false, meaning not a prime number. But it was never able to tell us the factor. Okay, so Miller-Rabin is actually testing whether a number is prime or not, but it has no way to tell us the prime factor consistently. There may be cases where it is able to find pairs of squares, right, as shown earlier. But for large numbers, finding such witnesses turned out to be an open problem. Okay, in fact, quantum computer turned out to be good at solving that kind of problems. Finding the period where 2 numbers square or equal is quite a fascinating number theory, group theory problem. Okay.